Imagine you're just standing on the sidewalk, right, looking at this really beautiful house.
Okay, I'm picturing it.
Yeah, so you can see the color of the paint, the trim around the
Right.
windows, the shingles on the roof, and it looks totally solid, complete. But, like, what if I told you that literally everything you can see or touch, the paint, the trim, all of it is just this tiny, tiny fraction of what's actually there?
I mean, that would be a little unsettling.
Right. What if you were completely blind to the bricks, the steel beams, the massive concrete foundation that's actually holding the entire structure up?
Well, I mean, that would completely change how you understand how that house stands up and, more importantly, how it might eventually fall apart.
Exactly. And that is literally what is happening every single time you look up at the night sky. Everything you can see is just the paint.
Yeah, just a very surface layer.
So today, our mission on this deep dive is to map the invisible architecture of the cosmos. We're going to go out and find the bricks.
It's a fun project.
It is. We're going to question what those bricks are actually made of. And then finally, we'll look at how that completely invisible foundation will, ultimately dictate the literal end of time.
Which is just a massive, massive journey. And to get us there, we're pulling from a really fascinating stack of recent research.
Yeah, some really heavy stuff.
It is, but rather than just, like, reading through a dense textbook, we're going to connect the dots here. We've got recent observational data on gravitational lensing, plus this radical new astrophysics theory that literally attempts to rewrite how gravity works.
Wow.
Yeah, and we're tying that into comprehensive models mapping out the ultimate, doomsday scenarios for the entire cosmos.
Okay, so let's unpack this,
All right.
because I feel like we have to start with the foundation itself, right?
Right.
For decades, scientists have been telling us that roughly, 5/6 of the material universe is just completely invisible to us, dark matter.
Yeah, 5/6. It's a huge
Mhm.
majority.
And it doesn't emit light, it doesn't reflect light, it doesn't even interact with electromagnetism at all, but it acts as this, like, gravitational scaffold for the whole universe.
I actually love that term. Scaffold is just the perfect way to look at it because, if we rewind the clock to the very early universe, like right after the Big Bang, things are just incredibly hot and dense.
Right.
And ordinary matter, which physicists call baryonic matter, so that's the stuff that makes up you, me, the stars, everything we see.
The paint on the house.
Exactly, the paint. That ordinary matter was strongly interacting with radiation. And that radiation was exerting this massive outward pressure.
It's kind of like a wind blowing sand away before it can even form a dune.
That is a brilliant visual, actually.
Oh.
That radiation pressure was just so intense, it functioned like this crazy cosmic hurricane.
Wow.
It completely prevented ordinary matter from clumping together to form any kind of structures. Like if the universe only contained ordinary matter, that radiation pressure would have totally won the battle.
So no galaxies.
Zero. Galaxies never would have formed. No Milky Way, no Earth, no us. We would all just be this diffuse, even soup of particles, just spreading out forever into the void.
But dark matter doesn't interact with that light, so it just completely ignores the radiation wind.
Right, exactly. Because it operates totally outside of electromagnetism, dark matter was able to decouple from that intense radiation super early on.
Okay.
So while all the ordinary matter was getting blown apart by the wind, the dark matter started quietly clumping together under its own gravity.
Oh, I see.
Yeah, and it created these massive invisible halos, which are essentially just deep gravitational wells. Then later, when the universe finally cooled down enough and that radiation wind died out, the ordinary matter simply fell into those invisible wells.
Oh, wow. So the dark matter built the scaffold, and the visible universe just kind of settled into it like dust.
Precisely.
Okay, but I'm a little stuck here. You're telling me this scaffold ignores light completely.
Yeah.
So how on earth are cosmologists out there mapping something that is literally invisible?
Well, we map it using the one thing dark matter actually does interact with, which is gravity.
Mm-hmm.
And to really understand how that works, we have to look through the lens of Albert Einstein's general relativity.
Right, good old Einstein.
Always comes back to him. So Einstein taught us that mass actually warps the very fabric of space-time,
Okay.
which means when light from a distant galaxy travels toward us, it doesn't move in a perfectly straight line if it passes a massive object on the way.
Because the space it's traveling through is curved.
Exactly. That warped space-time physically bends the path of the photons.
I just love this concept. It's called gravitational lensing, right?
Yep.
It's sort of like looking at a candle flame through the curved base of a really thick wine glass. Like you can't see the glass itself directly, but you know its exact shape and its thickness just by looking at how the flame of the candle gets all stretched and distorted as you look through it.
That is exactly how observational cosmologists treat it. And they use this trick in two distinct ways. The first is called strong lensing. And this happens when you have a massively dense object, like a huge cluster of galaxies, sitting perfectly between our telescopes and a light source way further in the background.
So it's right in the way.
Right in the way. And the gravitational field there is so intense, it severely bends the light, creating like multiple mirrored images of the exact same background galaxy.
Oh.
Or it stretches it in these long, glowing, curved arcs.
Yeah, the sources actually mention this one supernova, IPTF 16U.
Oh, yes.
And we literally saw multiple images of the exact same exploding star just popping up in different places, all because this invisible mass in front of it was bending its light in different directions.
Oh, it's wild, isn't it?
It's totally like cosmic funhouse mirrors.
It really is. And if the alignment is absolute perfection, the light bends into a complete circle, which we call an Einstein ring.
That is so cool.
It is. So strong lensing is fantastic for probing the dark matter substructure within really specific massive galactic halos. But perfect alignment like that is incredibly rare.
Right, the universe doesn't just line things up for us.
No, it definitely doesn't.
Okay.
So to map the invisible scaffold across the entire cosmos, we have to use something else called weak lensing.
Which I imagine is much harder to spot.
Oh, much, much harder. Weak lensing looks at subtle, almost imperceptible distortions in the shapes of literally millions of distant background galaxies.
Wow. Millions.
Yeah, it's a massive statistical game. By looking at this coherent distortion, which we call cosmic shear, across vast patches of the sky, researchers can basically mathematically reconstruct huge mass maps of dark matter. It shows us the cosmic web itself.
But hold on, the sources highlight some pretty major complications here. Specifically, there's this thing called mass sheet degeneracy and projection effects.
Yes.
So if we are taking this massive three-dimensional universe and essentially squashing it into a two-dimensional projection on our telescope lenses, I mean, how do we know we aren't being completely fooled by overlapping cosmic mirages?
Well, it's a highly valid concern. Honestly, it is the nightmare scenario for anyone trying to map the universe. So mass sheet degeneracy basically means that mathematically, you can take a lens model, scale the mass up, add a uniform sheet of mass across the whole field of view, and it will produce the exact same visual lensing effect.
Wait, really?
Yeah. Think of your wine glass analogy.
Yeah.
If the whole glass is uniformly thicker, but the curve is scaled proportionately, the candle flame might look distorted in the exact same way.
Oh, I see.
Plus, as you mentioned, projection effects mean you can't always tell if you're looking at one massive dark matter clump or just several smaller halos accidentally stack along the line of sight.
Right. So if the math actually allows for totally different physical realities to look identical to our telescopes, how do we trust any of these maps?
Well, this is where we have to bring in outside context. We don't just look at lensing in a vacuum. We cross-verify with other cosmological probes, specifically the cosmic microwave background or the CMB.
Ah, the leftover radiation from the Big Bang.
Exactly. Think of the CMB as the ultimate, most distant wallpaper behind everything in the universe.
Okay, wallpaper.
And we know exactly what the statistical pattern of that wallpaper should look like. So if we look at how that specific wallpaper is distorted by the foreground glass and combine that with how the closer galaxies are distorted, it essentially gives us back our depth perception.
Oh, that makes sense.
Yeah. When you layer the lensing data over the CMB data, it solves that 3D projection problem. It breaks the mass sheet degeneracy, and we get a totally trustworthy blueprint of the scaffold.
Okay, so here's where it gets really interesting.
Yeah.
For decades, the standard cosmological model has just assumed this scaffold is made of physical particles, specifically WIMPHs, which is weakly interacting massive particles.
Right.
But despite literally throwing billions of dollars at these highly sensitive underground detectors and searching for decades, we have never found a single one.
Not one.
Which brings us to the second part of our sources, this incredibly fascinating paper on Merzakalov gravity.
Yes. So this paper asks a deeply uncomfortable question for modern physics.
Uncomfortable?
Well, what if dark matter isn't a thing at all? Like, what if we've spent decades hunting a ghost particle when the real culprit is just a fundamental misunderstanding of gravity itself?
Okay, the paper introduces this concept of a Weizenbuck spacetime.
Yes.
And up until now, Einstein's general relativity has basically relied on the idea that gravity is the curvature of spacetime. But this modified gravity model introduces a totally new mathematical scalar called torsion, represented by the letter T. And I'll admit, this is where my brain started to hurt a little bit.
It's dense stuff.
It is. So help me visualize curvature versus torsion.
Okay, so to really understand this, we have to look at the geometry of space. In Einstein's model, mass creates a dip or a curve in space-time.
Right.
You always hear that classic analogy of a bowling ball resting on a trampoline. The fabric stretches down and other objects kind of roll toward it.
Yeah, we've all seen that one.
Right. But in a Weizenbuch spacetime, we aren't just looking at the stretch. We are looking at a geometric twist or torsion in the fabric itself.
So instead of dark matter being invisible sand that's like dumped into the cosmic sandbox to create extra weight and extra gravity, it's like the sandbox itself is fundamentally twisted.
That is a really great way to put it. The theory basically argues that the mathematical properties of this geometric twist act dynamically.
Okay.
So in regions of very high density, like the areas right around galaxies, this torsion becomes dominant, and mathematically, this twist behaves exactly like a pressureless fluid.
Interesting.
Yeah, so it mimics the gravitational effects of dark matter flawlessly.
And this solves the galaxy rotation problem. You know, the fact that stars at the outer edge of a galaxy are spinning way too fast to just be held in by the visible mass.
It does. The geometric twist actually provides that extra gravitational grip, which explains why those really fast-moving outer stars don't just completely fling off into deep space.
Wow.
Yeah, it explains those flat rotation curves without needing to invent a single new invisible particle.
Okay, but in the sources, there's a lot of pretty heavy jargon about how they actually proved this. Like, they mention a Markov chain Monte Carlo analysis tested against Spark's data. You're going to have to translate that for me.
Fair enough. I can do that. So Spark is just a massive observational database of how different real galaxies rotate.
Okay, easy enough.
And a Markov chain Monte Carlo analysis is basically just a really complex way of running millions upon millions of statistical simulations.
Got it.
So what they did is they took their mathematical theory of a twisting universe, fed it into a supercomputer, and asked it to simulate thousands of different galaxy formations to see if it actually matched reality.
That did it.
It did. It matched the actual observed data of real galaxies beautifully. It replicated literally all the key features we currently attribute to dark matter.
Hold on, I have to push back here.
Okay, go for it.
You can't just change the rules of gravity to make the math work. Doesn't that completely break the fundamental laws of physics?
That is a very valid point.
Like, what about the conservation of energy and momentum? Energy can't be created or destroyed. Aren't we just kind of cheating the math to get the result we want?
Well, that is the exact question every physicist asks when they hear the words modified gravity. It's actually the reason so many scientists are deeply skeptical of these kinds of theories.
I don't blame them.
Right. And in many earlier models that tried to modify gravity, you really did run into massive conceptual issues. The conservation laws just broke down. Energy was basically leaking out of the equations.
Which is a cardinal sin in physics.
It really is. But this specific paper actually avoids that trap entirely by using something called a veil beam approach.
Okay, another intimidating term. What does a veil beam approach actually do?
It sounds scary, but think of it like laying down a hyperflexible mathematical grid over our twisted sandbox.
Okay, a grid.
Even though the sand or the space-time is twisting and shifting, this grid is specifically designed to track every single point of energy perfectly. It adapts to the twist without losing its internal logic.
Oh,
Yeah, by treating the twisting geometry and the coordinate grid as completely independent mathematical objects, they derive a set of rules where energy and momentum are locked safely in place.
so it tracks it all perfectly.
Exactly. It preserves the conservation laws, not by ignoring the twist, but by basically building a smarter measuring tape. It doesn't break the rules, it just expands the geometry of the rules.
Wow, okay, so whether it's ghost particles or this twisted geometry, cosmologists are clearly just obsessed with measuring exactly how much of this invisible weight actually exists.
Absolutely.
And why? Because the universe is locked in this insane cosmic tug of war between the outward push of expansion and the inward pull of gravity. And the sheer amount of this invisible weight is going to determine who wins in the end.
Yes. The ultimate fate of the universe is just a question of geometry, really, and that geometry is entirely dictated by the universe's total density.
Right.
So we combine the density of ordinary matter, dark matter or torsion, depending on which model you like, and dark energy. And we call this total value the density parameter, or omega.
And the value of omega gives us three possible shapes for the universe and three very different doomsday scenarios. It's
Right.
like throwing a ball into the air. Does it fall back down to your hand? Does it just keep floating upward forever? Or does a hidden rocket strap to it and just tear it to shreds? Let's start with the first one. What happens if omega is greater than 1?
Okay, if omega is greater than 1, the total density of the universe is high enough that the geometry of space is closed. It's curved in on itself, sort of like the surface of a perfect sphere.
Okay.
And in this scenario, gravity eventually wins the cosmic tug-of-war. The expansion of the universe will eventually slow down, completely stop, and then reverse.
So the ball falls back down to your hand.
Precisely. Everything starts rushing back together. Galaxies collide, the background radiation compresses and heats up to just unimaginable temperatures. And eventually, literally all matter in space-time collapse back into a super dense, incredibly hot singularity. We call this the Big Crunch.
The ultimate reset button, which I guess leads to the idea of the big bounce, right?
Yeah, exactly.
The concept that our Big Bang was just the immediate aftermath of a previous universe's big crunch. Just this endless cycle of cosmic breathing.
That's the cyclic model, yes. But I should point out, that requires dark energy to not be a major factor or to somehow eventually reverse its behavior and pull inward.
Which brings us to the second scenario. What if omega is less than 1?
Okay, so this is the open universe.
Shaped kind of like a saddle, right?
Right, a saddle shape. If the density is that low, gravity is just too weak and the universe expands forever. But it's not a gentle, peaceful coasting.
Oh, no.
No. If dark energy, which remember is this mysterious force accelerating the expansion of our universe right now, if that keeps getting stronger over time, it leads to the big rip.
The hidden rocket tearing the ball to shreds. I'm not going to lie, this is the darkest one to me. Explain how this actually happens, because the mechanics of it are terrifying.
It is terrifying. It basically happens in stages, as the expansion rate of space itself eventually just overwhelms all other forces of nature. So first, galaxies are torn apart, because the gravitational pull holding the stars together just can't compete with the space expanding between them.
Wow.
Then solar systems are unbound. The literal space between our sun and the Earth expands so fast that planetary orbits just completely fail. Planets are ripped away into the dark.
And it gets smaller from there.
It does. Eventually, the expansion becomes so violent that the electromagnetic and strong nuclear forces are just overwhelmed. The very atomic bonds holding the matter in your body together are physically ripped apart.
That's crazy.
The atoms themselves dissolve into unbound elementary particles. Space-time essentially just shreds itself into pure nothingness.
Okay, well, moving on from that complete nightmare. The third scenario is actually the one our current observational data supports, right? The Wilkinson Microwave Anisotropy Probe, or WMAP, basically confirms that our universe is essentially flat. Omega equals exactly 1.
Yes, a flat universe is perfectly balanced. But because of the constant push of dark energy we were just talking about, a flat universe will still expand forever. Just not violently enough to actually rip atomic bonds apart. Instead, it leads to the big freeze, which is also known as heat death.
The ball just keeps floating away, getting colder and farther, literally forever.
Yes. The universe expands and cools asymptotically toward absolute zero. Over trillions of years, all the gas clouds needed for star formation are completely exhausted.
Right.
So the stars just burn out one by one. The entire universe goes totally dark. The only things left are black holes. And over unimaginable stretches of time, even they slowly evaporate away via Hawking radiation.
It's so bleak.
It is. The universe reaches maximum entropy. Basically, everything is evenly distributed, with no energy gradients left to do any work, spark any heat, or sustain any life whatsoever.
But the sources actually mention a fascinating counter-idea to this by the physicist Freeman Dyson.
Oh, yes.
Dyson's eternal intelligence. He theorized that in this totally freezing, expanding universe, an ultra-advanced intelligence could actually survive forever by just endlessly hydrating.
It was a beautiful, really optimistic idea, actually, because Dyson realized that computation or just having a thought costs energy.
Right.
So in a cooling universe, the ambient temperature constantly drops. If a machine or an intelligence can operate at a lower and lower temperature, it actually requires exponentially less energy to process a single thought.
So they would basically wake up, process a single thought, expend a tiny amount of energy, and then go back to sleep for like eons while the universe cooled further,
Exactly.
lowering the energy threshold required for their very next thought.
That was the hope. But unfortunately, the discovery of accelerating dark energy just basically ruins the math on this entirely.
Really?
Yeah.
Why does dark energy ruin it?
Because space isn't just cooling, it's expanding faster and faster. This means distant regions of the universe will eventually become completely causally disconnected,
Meaning what, exactly?
meaning the galaxies and energy sources around you recede away faster than the speed of light.
Hmm.
So the energy required to go out and gather resources, or even just communicate over those massive expanding voids, it becomes totally impossible.
Oh, wow.
Yeah, your resources basically flee faster than your energy needs drop.
Hmm.
Dyson's infinite hyconation requires a universe that is just gently cooling, not an accelerating, isolating one that completely strands you in a dark void.
Okay, so crunch, rip, or freeze. Those are the big three. But the sources throw one massive wild card into the mix.
You sure do.
A scenario that could happen at literally any moment, regardless of the density of the universe or the shape of the dark matter scaffold. The big slurp.
Yes, also known as false vacuum decay. This is rooted in quantum mechanics and the Higgs field.
Right, the Higgs field gives all fundamental particles their mass. And this theory suggests that the Higgs field might not currently be in its absolute lowest possible energy state. Like, it might be sitting in a false vacuum. I kind of like to picture it like a ball just resting in a small dimple on the side of a very steep hill.
That's the exact physics analogy people use. It's perfectly stable for now, just sitting comfortably in that little dimple. But quantum mechanics tells us about something called quantum tunneling.
Okay.
This means that at any random moment, a piece of that field could spontaneously just tunnel right through the lip of the dimple and roll all the way down to the true bottom of the hill, what we call the true vacuum state.
And if that happens,
If that happens anywhere in the cosmos, it creates this bubble of true vacuum that expands outward at the exact speed of light.
and inside that bubble, the fundamental laws of physics are entirely rewritten. The physical constants just change.
Completely.
Matter, energy, the bonds between atoms, everything we know is instantly annihilated and replaced with something totally alien.
Yeah.
So if this vacuum decay happens, would we see it coming? And more importantly, would it wipe out the entire universe?
Well, we absolutely wouldn't see it coming. Yeah, because the bubble expands at the exact speed of light. And information cannot travel faster than light, so the literal destruction of your atoms would arrive at the exact same instant as any visual warning.
Oh, wow. Okay.
But to answer your second question, no, it wouldn't wipe out the whole universe.
Wait, really? If it expands forever at the speed of light, why doesn't it consume everything?
Because of the very dark energy expansion we've been talking about. The metric of space itself is expanding so fast that galaxies more than roughly 13 billion light years away from us are currently receding at speeds faster than light.
Oh, I see.
Yeah. So even though the big slurp bubble travels outward at the speed of light, it literally cannot catch up to the outer edges of the expanding universe. The empty space between the bubble and those really distant galaxies is being created faster than the bubble can cross it.
Okay, that is strangely comforting in a very bizarre way. Let's look back at the incredible ground we've covered today.
We've covered a lot.
We really have. We started by exploring how cosmologists are trying to map the invisible scaffold of the cosmos, right? Learning how scientists use the bent light of gravitational lensing and the cosmic microwave background to find the weight that actually holds galaxies together.
Right.
We question the very nature of that scaffold, exploring how Mirzakalov gravity suggests dark matter might not be a missing ghost particle at all, but a mathematical geometric twist in the fabric of space-time itself.
And finally, we saw how the total density of that invisible weight, fighting constantly against dark energy, dictates our cosmic destiny. You know, whether the universe is a heavy sphere that crunches back together, a saddle that rips itself down to the atomic level, or a flat sheet that basically freezes into a dark eternal void.
It's undeniably heavy stuff. But before we go, what stands out to you from all this research? Is there a final thought in all this cosmic doom that offers a different perspective for you?
Actually, yeah, there is.
Yeah.
And it comes from the bleakest scenario of all, which is the big freeze. So let's say the universe expands forever, the black holes evaporate, and we reach a completely dead state of maximum entropy, absolute zero, pure nothingness.
Right.
What's totally fascinating here is that according to the rules of quantum mechanics and statistical thermodynamics, specifically something called the Poincaré recurrence theorem, maximum entropy isn't actually a static permanent end.
Wait, what do you mean? How can a dead universe not be permanently dead?
Well, because of random thermal fluctuations. Over a timeline that is truly infinite, probability basically dictates that entropy can and will spontaneously decrease.
Really?
Yes, Particles in a totally random, dead void will eventually, through sheer endless statistical shuffling, just bump into each other and form structures again.
Oh, wow.
Yeah, given an infinite amount of time, it is mathematical certainty that out of an endless dark void, the exact specific arrangement of particles, atoms, and synapses that makes up you, listening to us right now, could just randomly assemble itself again.
So even in the absolute death of everything, the math says that you could just, like, pop back into existence to do this all over again.
Exactly.
That is a truly mind-bending concept to leave you with. Thank you for joining us on this deep dive. The next time you look at a house,